Here we go. Welcome to fall 2020, the alternate version. So physics 390, computational physics. In my case, that means mostly astrophysics, but that's where my examples come from. That doesn't mean that this is only useful in astrophysics. It is a very general course. Basically, you start with data, you have a model, compare the two. How do I visualize that? These are all the basics that you really need to know as a scientist. And honestly, it's the same problem every time. So it doesn't matter if you're a social scientist or a physicist or an astrophysicist. You have data. You need to understand your data. You need to show your data to other people. And you need to compare it to a model. So this is me, Ben Holverda. And I'm trying to figure out if this, here we go. Here's how you can reach me. Honestly, email is the best. Tentative office hours by appointment and much trepidation. Honestly, I'll just do Zoom calls with anybody who has issues. There is no required text, but I will give you lots of, like, hey, this is a pretty cool thing, but none of them really seem to hit the mark for me. All right. Okay, today, what the, is this? Right, this thing is going very... All right, gave you new batteries and still annoying. OK, so today we'll talk about how the class works mostly, and we start our Jupyter Notebooks assignments. Really, this is like how we set this up. This is the Teal Room. Welcome. Hi. And we start like, how do we start this? There are Mac Minis to the back of every single computer here, so you can use them. If you are stuck on something, your computer has melted, all that good stuff, feel free to use these. I will be here on Mondays, and I will be here on Wednesdays, and I'll do everything online on Fridays. So class setup. Monday, we go over a topic. So Monday is me talking. I don't feel it's a good thing for me to be talking the entire week. So Wednesdays and Fridays, we work for the individual notebook assignments. These are on GitHub. They're also on the Blackboard for this class. So it doesn't matter where you get them from. They should be the same. At least I uploaded them at the same time, so they should be the same. For the midterm, we pick a recent 2019, 2020 is fine too. Astronomy or physics paper or anything else. Actually, I've loosened this up a bit. Pick a paper that you like. Pick a paper that you've read. Pick a paper that you've heard about. But I don't want you to go, oh, if I have this press release. Press release is great, but there should be somewhere in the bottom of the press release this is the scientific paper this was based on. And then you go in and go like, oh, here's the crux plot. Like, here's the plot that shows the result. Here's the thing. Here's the result in a neat little package, preferably without any. I can just throw it up, and it's clear what it's about. So that's the one you pick apart. You pick apart and go like, OK, what do I like about this visualization? Why does this jump out at me? Why does it convey everything perfectly? What are they hiding is the next question that you need to go and ask yourself. Because every visualization hides detail. You have to remove detail, because otherwise nobody can, it overwhelms. So you really need to pick apart a visualization, and I'm doing that as a paper because talks are a little too tricky right now. And then we do a final exam on all the topics. Basically, everything passes the review. The nice thing is it'll be on your laptop. It'll be a time coding assignment, but essentially Google anything you need, take your notes, grab your old Jupyter notebooks, go like, wait a minute, we did that in assignment number 5. Run to assignment number 5 and go do that. It is absolutely open everything, OK? Because guess what? That's how you're going to code in the real life, right? Nobody is going to shut down Stack Exchange on you. At least I hope not. So Monday's the lecture. We record this, so I hope you're all OK. There's I'm talking to there. And so that's what's going to be on the recording. Wednesdays, I'll be here. So if you require another machine, I will be here. You can work through the Jupyter Notebook. I will shout instructions at you from 6-foot distance. And you can do the class that way. Lots of people have their own laptops, so you can do the class that way. I'm fine with that. Me and Lutz will support machines here. If your machine is possessed for some reason, good luck. I am not supporting a Windows environment that I haven't worked in since 1995. So, sorry. Okay, and so Friday will be online only because essentially we'll just do Blackboard Collaborate and work through any remaining issues. This is the Tila room. There shall be no snacking in the Tila room. There shall be no drinking in the Tila room because this is a computer environment and we'd like to keep them clean. Well, now since we're all, mass-caped crusaders, we don't really have that problem, but it's definitely something that I need to emphasize. Need access, let me know so we can work something out. If you kind of go like, I am just working on these Mac machines and I don't have my own computer or it broke, we'll work something out. We'll work something out with Dr. Habersaddle. All right, so the COVID rules. Thank you all for wearing a mask. Thank you all for sitting at different tables. Thank you all for being as antisocial as you should be. And then clean the workspaces. That's what this is here is for. There's spritzers and wipes so that you can wipe off the workspace as you leave. So all the work is handed in through Blackboard. So or you can email it to me. So I am not touching anything. The good news is it was Jupyter Notebook, so I wasn't touching anything anyway. But I really am not interested in permission forms and anything like that. You just email it to me, and I'm emailing it back to you all signed. We're going completely paperless. This is the thing that pushed us over the edge. Yes, question? All right, cool. There, masks are mandatory. Let's see if anybody got this reference. Yes, the fellow old person in the class knows this reference. Nobody else has seen the... Anyway, you can't be doing that. That is my phrase. You can use that to me as well, right? If I am just cheerfully, whipping off my mask and shouting at everybody, you say, you can't be doing that, and I will stop, reconsider. That's it. This is the magic phrase. This is a textbook that you can use. It is incredibly useful if you are starting. It was written by a grad student, which honestly most of the best documentation comes from. People who got annoyed that this wasn't written down somewhere, wrote this down, and now it's written down, so it's great. And so it's free. This is on Blackboard for you to download. It's a PDF. It just introduces you to things like a Unix environment, like a terminal. This is what we need to figure out how to navigate a command line interface, right? So we do a lot of stuff over the command line interface because it's so powerful. It's also so powerful means that if you mess up, that's it, right? So instead of if you hit delete on the command line, it is gone. If you accidentally drag a file into the trash, you can just quickly get it out. There's always like I can do Control Z or like backspace or something. Command line, not so much. So it's a less forgiving environment as well. All right, so Jupyter Notebooks. So there are individual notebooks. So Jupyter Notebooks are kind of their own little coding environment where you can alternate markup text and code, and then execute code in little cells. This is great for learning. This is great for prototyping. This is fantastically not so useful if you are doing like huge computational project, right? Then you are going back to basically a text file with .py at the end, and you execute the whole thing in one row. But it is really useful to iterate over things where you, like, for instance, want to improve your plot. And you're like, actually, that should be a slightly bluer shade of blue. You can just keep doing that. Possible to do them at home, but you do need an Anaconda or Astroconda installed. Astroconda is the base package for most modern astronomy. So again, I'm teaching this because I'm an astrophysicist, and this is my example of your specialty specific package. You definitely have this for particle physics. You definitely have this for social sciences. You definitely have this for machine learning. Oh God, do you have more than one for machine learning, right? So there's lots of these packages. But most of this is quite simple code, right? Most of this is principles, not the hard-working code that you're probably going to write for your PhD thesis, right? So, all right. Wait, I get to Google? Yes, absolutely. The fact that when somebody asked this on Stack Overflow has already asked that very specific question and somebody answered it is wonderful. It is just a community, and so please contribute to said community as soon as you are able. And that's because, you know, as soon as read documentation. It doesn't mean that you read documentation from A to Z, but as soon as you start working on something, you just keep referring to the documentation. The documentation is your first stop. So the reason that I do this class this way is because I'm trying to get some healthy habits into you. And the healthy habits are, A, I don't have to solve this all on my own. Somebody somewhere on the great miasma that is the interwebs has probably answered and asked this question. And 2, I wonder if this is in the documentation. Probably. Documentation is really important, and so modern code has a lot of detail of what it is supposed to be, partly because the developers who are making the code are communicating this way. So they agreed, like, this is what this function does. So it gets really specific. What goes in, what comes out, what you can expect, what actually is computed inside. It doesn't sound like a lot, but it's really useful if you've got, like, a statistical test. So the class goals are, in all physical sciences, we take data. I can actually just scrap physical, right? Most sciences take data. We compare them to models, and then we make predictions for future. So those are the 3 components that we're really going with. Data, modeling, prediction, because that's how the scientific method works, right? We've got data, we've got a theory, or if we've got a hypothesis that explains all it, that's our model, and then we make predictions, and those predictions can then be tested. Data quality, model comparison, and visualization are key components in that, and so that's where we're going to focus on. Okay, so model versus data. Models are incredibly well described. You can literally say, like, A, B, and C go in. Those are my parameters. This is what they mean. 0 error and uncertainty. I can be as precise as I want. I can give you, there's some modelers who really go overboard and go, like, here's my 9 digits behind the, you know, the significant digits that I can give you for my model. That's great, but my data is, you know, noisy as anything. And it's so infinite precision is possible, but not really useful because you're comparing it to data which is inherently empirical, always has a noise component. This is a thing that I find people find very hard to accept sometimes. Like, but I can do a better measure. Yeah, but there's still going to be a noise component. There always is a noise component. If anything else, whatever you're measuring with will have thermal noise. If everything else has been eradicated, there's going to be thermal noise. There always is thermal noise. So may contain more than one driver than we know. The driver that I mean here is that you have a couple of model parameters, and they explain most of the data, but in the noise, there might be an additional pattern that is actually driven by a 3rd or 5th or 18th parameter. Noise need not be random. So that's something that we need to check. And so as the visualization, the model parameters, the fitting, all that stuff is basically comparing one to the other. And we have so I am going to hopefully give you a toolbox that says, so my whole idea was like, there's going to be a professor in your future that just throws a data file at you and goes, compare this to this model. And then you go, great, I have the tools to go do the job. That's the plan. So there's always an XKCD for that. That is, I would say, some of my teaching philosophy here. They usually have, this is an ex-physicist who basically started illustrating with stick figures how various modeling issues with computers, but also like, I particularly like this one because you've got model, model, model. Essentially, they're overfitting here. This would be a polynomial, slightly different polynomial. This is an exponential. God knows what's happening here, right? But there's usually a point to this, which is, but funny, but there's a point to it as well, which is essentially saying, oh, we've overfit the data. You may have noticed that in the news, we currently are talking about data a lot more than we were, and a lot of people have been overfitting these to the point that, you know, various data scientists will stroke out saying, like, you can't be doing that. So What's the final grade? 50% the Jupyter Notebook assignments. If you blow through all of them in the first week, good on you. I don't care what speed you're doing these at, but I have spaced them out for once a week. So if you suddenly feel the urge and do most of them, great. I just need them from you before the final. 20% is that oral presentation or paper. If anybody really doesn't like writing, you're perfectly okay to give me like an oral presentation if that's like more your thing. I had to do the other thing around with my 590 class a while back. So if like, yeah, I can't stand in front of a crowd, then you can write it down on a paper, whatever you're comfortable with. But I was going to go with paper because that's a little easier with, these days. And then 20% is the final. So basically, you know if you've got this class well before you get to the final. That's always my goal. And so you start with 10 points of good citizenship. Basically, don't be an unpleasant person in class to anybody else. My rule 1 for teaching is do not impair the learning of others. And so as soon as you do that, then I'm going to like, well, that's, puts those 10 points at risk. That's it. It's very simple. There is extra credit. So if you feel inspired by the stuff that we've done, or you've got some of your own data, or you go like, oh, I really wonder if I can plot this, for example. I occasionally have that itch as well. So if you make your own visualization using a Jupyter Notebook and you just share that with me, that could totally be an extra credit. So if you're feeling like, oh, I'm doing a research project and I totally use this, or I'm doing this other class and I've used the tricks that I've learned. Look, great. That's definitely extra credit. All right, I have a question. This is totally out of my 100 level class, as you can tell. Is it in the syllabus on Blackboard and the U of L website, provided in class, or easily Googleable in 20 seconds? Then I'm just going to wait until you figure it out that you can Google it. I might not answer. Other than that, I do email 9 to 5. Also, I think this is more relevant than ever. If your semester starts to catch fire, essentially, we have a grand plan for right now, and if it goes all wrong, please let me know because we can work something out. But the more time you give me before the end of the semester, the more wiggle room we all have. Okay? So this is important. If you start feeling like the semester is getting away from you, Calvin's desk on fire, let me know as soon as practical, because the reason for that is I'm willing to work with you. That's perfectly okay. All right. Right. So why Python? Sometimes I don't even have to explain that because everybody's like, yes, Python is the language. There are many languages. There are many computer languages. I started, and let's go date myself, with Pascal, who nobody has heard of anymore, thank God. Then I switched over to C++. I spent my misspent youth in IDL and a couple other scripting languages, but fairly early on somebody pointed out that Python was looking good, right? And the reason that Python was looking good is because we have many packages for scientific analysis. So the nice thing is that suppose you want a statistical rigorous test. Instead of hoping that whatever you found in numerical recipes and then code it up yourself doesn't have a bug in it, and then hopefully the test works, sort of, which you kind of understand, an actual mathematician, an actual statistician has written this thing, and now and other mathematicians have tested it. So it is absolutely tested, trusted code. This is really helpful if you want to go do other things. Like, so you're not a statistician. You don't want to be a statistician. I just need, I need the spanner. I need the statistical equivalent of a good hammer to go do this. That's it. So that's a really big strength of Python. It's also a scripting language, which means that it doesn't have a ton of parentheses and everything else. It works with indentation. So there's a broad online community with solutions. Again, Google the problem. You'll be surprised how many things have been answered already. And every subfield has specific packages. So that's another useful thing. So if I'm working in like generic Python, then I'm doing some astronomy related stuff like cosmology packages. I'm like, I need to figure out what redshift a few billion light years is. Then I can go do that with the functions that are in my AstroPy package. And I go back and do a bunch of machine learning because I also imported a machine learning package. And I can do everything in the same script. There's no code hopping. There's nothing like that. So you can actually keep everything pretty contained. This is a really big strength of Python. There are other packages that have, for instance, R is slightly better, I hear, statistics-wise. They have a few more tools. Then there are things like Julia, which works on GPUs. Like there are many. There's no reason that you have to stick to Python. Python neatly bridges the easy to learn and easy to expand and a big community that can help me. That is really like, if you're a beginning scientist, that's where I would run to. However, there might be specific things we go like, yeah, I'm sorry, I'm doing really big computations. It has to be fast. Well, then you do Python, for instance, with crunchy C-bits, is it's called. So like you optimize speed, and then you call it from Python. Python is a good way to make pipelines, for example. So a lot of things that we do in science these days is that we have a machine that measures something, and then a whole user base that just wants to see what the results are. So a lot of things happen to the data before we can actually give it to our user base. Those steps are fairly standard, right? They need to get rid of known artifacts in the detector. Things like, oh yeah, if you're the LIGO, the gravitational wave detector, for example, you have a thing like, oh yeah, that chop that bit out because that's when a truck drove by. Those things are pretty much prescribed. So that's called a pipeline. It's literally the data goes through this pipeline, and so scripting languages like Python are used for pipeline production a lot. So, okay, so I'm going to give a brief overview as an example because this is the one that I'm the most familiar with. Again, sorry, I'm an astronomer, not a real physicist, yada, yada. Here's the AstroPy overview. So the core package is community-driven, so it means that lots of different people have contributed to this. This is very typical for Python. Open source, open development Python library for astronomy provides core functionality for more specialized astro packages. So people who do cosmology have given us like distances, the age of the universe at redshift 20, that kind of thing. Like I can just specify various cosmologies and figure out what that is. But also much more mundane stuff like figuring where stuff is on the sky. Now, if you've ever done trigonometry on a sphere, you realize that your eyes can start to bleed very quickly. It is really annoying to get just that cosine delta declination just wrong, and then suddenly you're observing right off the target. So getting that right, getting the right reference frames, which means basically where's 0 on this night sky, for example, 0, 0, 0, right? If you have a map, you go like, yeah, top down corner, for example, that's our 0.0. On a three-dimensional sphere, that's harder. Also, everything moves. So that's just an added bonus. So if you want to go from like how far away is that from that, AstroPy has all those things already solved. It is brilliant. So I don't have to deal with that anymore. So we have a core package. So that has units, for example. Astronomy is full of specialized units. We all measure everything in solar masses. We measure distances in parsecs. Then there are even weirder units like Janskys. And we have coordinates to transform the astronomical coordinates, as I was saying. Because we don't only have one coordinate system, we have many coordinate systems. We used to start with a coordinate system for every telescope on Earth. And we sort of started converging so that we can actually see what the other person was looking at. But there's lots of transformations that you need to do, and then there's time. Time does the same thing. How do you go from UTC to other times, not only time zones, but also astronomical times? And table. So I have one assignment in AstroPy table. Table is essentially where you ingest a data table. And since we in astronomy now are working with really large tables, this is no longer doable in Excel. It wasn't doable in Excel for a while now. So this is where you ingest data tables. So you import the data into your program. I have made one assignment with that. However, there are alternatives with that, so I will go and figure out how I can make this without using AstroPy. I will put the AstroPys on there right now. It's assignment 7. I will make an alternate version that you can use not using AstroPy table, but I think I'm going to use Pandas because that's what that is based on. Pandas is a data, again, one of those data sciences subfield things. All right. And fits. So here's, here's something that you will find in lots of science. Why are we doing it this way? And it's simply because we already did. So FITS is the original file image transfer system. This comes from somewhere in the deep 60s where we needed to move some data over and we needed to have a common format for data, for astronomical data to move about. And instead of having like, oh, well, a JPEG or a PNG or something, which is much more common for images, we went with FITS. And the reason for that is that it has a huge amount of metadata. It has metadata baked in right from the start. And the metadata, it cannot be longer than, I think, 32 bits because that's as much as can fit on a punch card. Yes, this is really old, but it's a standard, and a standard will stick around. Standards, people go like, well, I'm always used to doing this like this. So FITS standards have stuck around, and FITS has developed into basically a standard that's very useful for astronomers. And so we can still read the 1960s data and compare it to today's data. So I don't think this is going away anytime soon. So we made a FITS reader. So that's incredibly typical for just astronomy. We have this wonky, just specific to our science data file frame. And so we have a reader for that, and nobody else needs that, right? Nobody, no physicist ever needs to read a FITS table or data file. And if you're an astronomer, this is what you do all day. So open source means that it's free for everybody to use. Open develop means that everybody can contribute. So as soon as you become a pretty decent coder, and you've solved a problem. In fact, you don't have to be a terribly good coder. As long as you've got code that runs and does the thing that nobody else has figured out how to do, you can start contributing this. And then it gets vetted, and you improve it, and you also write some documentation so other people can use it. And that's a bit scary, but honestly, it's much appreciated by the world. And then if you're smart, you make sure that you have a paper that everybody can refer to, so they can say, like, yes, we've used the solution from so-and-so, and then everybody has to refer to your paper from now to eternity until somebody writes something better, which never happens. So there's affiliated packages. So you can write these affiliated packages. These are starting to happen so that you can write specific packages for specific instruments, for example. So these generalized packages are like, yeah, you can reduce a spectrum, for example. But now somebody is making a specific package for the spectrograph on this specific telescope. So you need to see if there's something like that. All right, so I use AstroPy when possible because I don't have to write the thing. So it's really, really, really pleasant. But particularly to your science, there will be a different package. If you have particle physics, for example, used to code exclusively in C, and it was very clearly prescribed how you did that, but now it's become, yeah, there's a Python package for that, so all done. All right, midterm, a paper where you go over scientific data visualization. So very important, give me context. You can't go like, I found this paper. Okay. Why was this important to you? Why is this important to me? Why is this important to society or the subfield or something, right? You've got to give me context. Why is this science important, and how does this visualization that you've now picked, you've picked one, right, in the whole paper. Papers typically have 20 or 30 or hundreds of visualizations, plots in there. But there's usually one that really brings the crux of the argument across. There's usually one, and you can identify because it's the one that they've worked the hardest, the longest, and looks the prettiest, right? That's usually the one that you want to take out. What are the strengths and the weaknesses of the visualization and the analysis? What would you do different? What would you adopt? And then summarize the impact of the visualization. So this is not simply like, I like the colors. It has to be like, all right, this is what I like about them. They've highlighted, everything is on there, but they've highlighted where the differences is with what they got before. Last year, people picked visualizations from all over, and so you can have like a medical paper. Please, let me know. There were sociology studies. Like, this is a data visualization course, essentially. So I don't particularly care where the data visualization comes from. So, for example, so we're not doing the presentation unless otherwise specified. If you are going like, I'm so much more comfortable talking rather than writing, okay, but please write. So, so we need the main conclusion of the paper. We need the main thing to get away with. And is what's the strength, what are the caveats, and context. So these are the things that I really am looking for. If I'm missing these things, then I'm like, all right, these are the things I've told you to put in there. MERP. Okay. For example, I'm now going to just give a talk like I'm giving the talks or the papers. We take W.E.B. Du Bois, who was a sociologist and critical for the civil rights movements. Essentially, he started collecting data. So data can be incredibly useful for the thing that you're trying to prove or the thing that you're trying to change. And so he is one of the first people who, this is all by hand with ink and pen, but neatly started drawing what the data told him. So starting from a table that he basically collected from asking people, he got, for instance, how much land use people have, or where that land use was, right? And try to visualize where the problem lies or what the improvement was. And I love these kind of things because you realize that essentially with Python we can do the same thing, but we're still doing the same thing. We're doing exactly the same thing. This is a bar graph. Bar graphs are fairly basic. The bar just curls. So they're really pretty, but they're not essentially quantitative, because it's going to be really hard for me to measure the length of every bar here. So, and I don't have an axis. So the axes are labeled, so it says here what's what. So this is the total value of what people owned, and it shows that over time it improved. So that's happening, but it didn't show, for example, how much it improved. It doesn't show me essentially what the x-axis is. So if I'm critiquing this, and again, pioneer in data visualization, right? He's just trying these things out. But if I'm seeing this in a modern paper, I would go, where's my x-axis? If I want to reproduce this data, if I want to measure what the actual value is, I have to go, I don't know, cut this out and and string it along and try to figure out what the x-axis is. So that's a problem, right? That's a problem in the visualization. The nice part is it is very visual, it's pretty, it's attractive, and it shows the main point, which is it's getting better. So what's the point that he's trying to get across? Is he trying to get across the exact amount of household, like how much the exact dollar amount? No. He's trying to get a trend across. And it's like, okay, so these are the two things, right? If I'm, for instance, an assessor or a tax office, I would like to know dollar amount, right? So that's when this is not going to work. The same thing goes for here. You want to compare two populations against each other. Visually, from a few steps away, you go like, okay, both of them have a big red, and then the big differences between the two populations happen in the other colors, really. So that's kind of like, that's the main point. And like you can say, like I see you nodding because you can see that from here. You can't even read any of the small print. However, if you want to get into detail, that gets harder. So see what, like, it's a good visualization because literally the person at the end of the room can see the main point without even reading the detail. It's like, okay, there's the issue, got it. But if you want to get detail and if you want to know more, is that detail available for somebody who goes like, oh, okay, that's interesting. I'm going to walk closer to that, right? So that's a good example of like poster visualization. If you do scientific posters, you know what I'm talking about. Scientific posters are a way that you show your work. And so if you want to show your work, you want to do basically this, right? Something to draw somebody in, and oh, there is more detail for me to explore. So that's a fantastic visualization for a poster. For a talk, however, most of you should be squinting trying to figure out what the hell is written here because that's way too small a font, right? So that's an issue. So there are pros and cons, and it depends on how you use it as well. Blank. So here's another example from causes of mortality. Again, showing how it improves or gets worse over time. And it's, again, pen and paper, but it shows what the main issues are in the army, because this was Florence Nightingale trying to convince people that, you know, basic hygiene while on campaign would be maybe a good idea. And a historian has made the next one. I really like this, even though it is really hard to read, because nothing says I can read this from a few paces away than, you know, curly script. That's just the worst. Sans serif font usually works the best for you know, any distance. However, this is Napoleon's army starting a land war in Asia. So this is the size of his army as he gets started, and as he goes along, this is the guys, the little black line is the guys that get back. So if you say like, oh, it was a disaster, how big of a disaster? Huge disaster, and you can see the disaster unfold. This is a bit different. This is kind of something between a map and a data visualization, and I think it's really well done. Considering this is a 19th century map, this is actually pretty cool. So those are kind of like the way that you can show data, and like you can get your one point across. Right? Nope. So the Jupyter Notebook assignments. They're all in Blackboard. They're also on GitHub. So here we go. If you want to do this here, do you want to do this here, or do you want to rather do this on your laptop? Probably laptop. Okay, so I'm going to run you through the thing for the machines here anyway. You can log on these. It's basically the user is the teal number that says on the top. The password is teal 2016 U of L. Log into your Wi-Fi with your own credentials, and then you start the terminal. So that is the command line interface. Who here has worked with the command line interface before? Cool, okay. This is fine. So the window where all the computer commands are typed, there will be a prompt. You type in a command, ls or cd. ls means like what's in this directory that I'm in. cd means change directory. And that command is executed after hitting return. We're going to execute two commands. On these, you need to do source activate astroconda. On your own machine, as soon as you start installing conda or astroconda, you need to now say conda activate astroconda. Astroconda is called the environment. So because we have all these different packages, you can have a Python installation with the Astro stuff installed, astroconda, and you can have, I have one for example, geological data, so, or geographical data. So CIS software, essentially GPS measurements, lots of points that I can now color in with, you know, pretty colors. And so I have that in a different environment, just in case the two installations don't play well with each other. So this tells basically activate the astroconda environment. So I am now going to work where all these things are preloaded. And then Jupyter Notebook, start my Jupyter Notebook. Where are you? Come on. If you've recently installed Conda on your machine, you do that with Conda activate astroconda. Make sure you install the astroconda environment. Again, if you didn't, let me know. I hope everything should be working for just plain Conda. As soon as it isn't, because I forgot, we'll work it out. But I'm making sure that you can just do this with plain Conda now. All right, so this is what that looks like. Source activate astroconda, you hit that, return, and then Jupyter Notebook, and then you hit return. And that starts the browser. If the browser is not awake yet, it'll start whatever the default browser is. And then on these machines, basically the terminal gives you an URL, and you copy and paste that into the window. On your machine, it might just start it up on its own. It does it with mine. And so you should now see a page where you can start navigating your computer. And that is your Jupyter environment. So you can now navigate to, this is what that looks like. I can now move to various directories, and that's where I look for the .pynb files. Those are Python Jupyter Notebooks. If you want to get all of them in one go simply to GitHub, my address, and then 39020F. So those are the ones for this semester. You can download the whole zip. It just comes down in one go. It has all the Jupyter Notebooks assignments and all the data files that you need. I did do a neat little trick so that we can download the bigger files, but now I'm realizing that those are all FITS files, so everybody who uses Conda cannot read them. Again, used to FITS files a little too much. So you move the directory onto your desktop, rename it with your ID if you want, and then move back to the Jupyter tab, because then you can just navigate there. All these Jupyter Notebooks are also in Blackboard. So you can just look at the week. Every week there's an assignment, and it has the accompanying data files. Either a CSV, which means comma-separated values, essentially a Excel notebook from back in the day. It's the easiest way to just separate values because nothing has a comma in it. Plain text files, which are simply rows of values, or a PNG. Yes, we're going to go work on a PNG image just for fun. And then you can upload your Jupyter Notebook that way. So you start a new Jupyter Notebook, you navigate to the Getting Started directory, you double-click on the .pynb file, and a new browser tab should open, and this is what you should see. Sorry for the long run to here's where the meat of the project is. Essentially, this is my solution. I do the whole thing, making sure that I have a solution for these things, so I know what it looks like. The solution is not in the GitHub repository. There's just the one without it, but this is what I want you to learn. There's some learning goals, some keywords, and then you put your name and ID in here. Preferably, I also put your name or an identifier here at the top, right? Because I'm going to see a ton of these things, and if I have exactly the same name, I have to go open all of them to figure out where yours was. So in the file and over here, you can double click. As soon as you click on these are cells. So you double click on these, you can edit them. These are basically HTML text, so you can type your name in there, and then there's like bits of text where I explain things, and then you can run code in some of the cells. Each cell is a snippet of code or the markdown language. It's not quite HTML. Double-click and activates a cell. Shift-Enter executes a cell. So basically, you can run code. You can run the cells out of order. This is both a blessing and a huge pain in the ass. Oh, sorry, I'm not so allowed to say that kind of thing. But it is a pain in the ass. For the following reason, if you define something in a cell, you say, my value, I just did this. Right? So usually when I'm warning you against things, it's because I have made these mistakes enthusiastically and with great effect. I defined the variable z equals a something in one cell, then I kept working, redefined z as something else, because z is such a handy I totally forgot that I had defined it up earlier. So it forgot the earlier definition and did it again. And then I re-executed a cell up there. And it goes, well, Z is something different now. And it gives me a completely different answer. And I have no idea where this problem comes from, just simply because I executed these cells out of order. So the fact that you can re-execute a cell over and over again means that you can fix your code, you can test it, you can prototype really quickly. The bad news is that as soon as you've made a modification somewhere below and you re-execute somewhere above, no idea what happened. So that is the fact that you can execute code out of order is going to bite you at some point, is my experience. So the trick is you can actually execute everything in one go, and it should run perfectly fine. Top to bottom, if things are defined in previous cells but not executed, Python doesn't know about them. If I say A is 5 in the bottom one, it doesn't know about them until we get there. And then it goes, OK, A is 5. But if I then go like, yeah, I want to do something in the top cell with A, then unless I've executed that cell, it's not going to know about it. Boom. Right. Need help. I will help. I will happily help. I will schedule a Zoom with you if you need. There will be issues I cannot solve because I'm not an IT professional. And again, haven't used a Windows machine since 97, I think. Yeah. So don't ask me about them. I have no idea what happens in them. So, and I've been this person who went like, oh, I have this really interesting problem. We go, oh, yeah, we know how to solve this. And they basically hand it back to me and say, like, it's haunted. Just burn it. So something might go wrong. Something will go wrong if it's your machine. Maybe you'll have to reinstall Python. I had to do that the other day. It's OK. It's very normal. All right, so we're done. Here we go. First name, last name, some kind of identifier. Upload on Blackboard is preferred, or you can email them to me. And then, but preferably only when Blackboard doesn't work. And then you need to log out of the Wi-Fi if you're working on one of these machines, because otherwise your credentials are basically running on a machine here that's just open for everybody to use. So I would not be happy with that. OK, so that is my adopted way to do a Jupyter notebook. We can start opening these things up. You can, or start installing Conda. Good code, by the way, this is something that is more a meta thing. You are your own collaborator. I cannot emphasize how often I was angry at myself 6 months spaced apart. What was I doing here? What does this thing mean? Variable names need to be descriptive. I said I had a variable name Z. Variable names should actually say what they are. So I don't know, confirmation underscore bias is a great variable name because it says what it is. It's OK to leave comments. In fact, please do so. Type up like you are writing to a mildly concussed self, right? Make sure that you leave comments, what you were doing, what you were thinking. These little markup cells are fantastic for that. I say, I'm going to do this. I'm going to measure that. I'm going to make this plot. I actually space out what my project is going to be in the first few markup cells. It's really useful because then I can go back. I'm doing this thing now. I'm doing this thing now. Like it's a notebook. It is a lab book. Graphical representation. I have lived through the PowerPoint MS Paint area. I can assure you that it is very terrible to just sort of try to finger paint your own graphs. So today we talked about how we get started, what we need to do. I will now go look at my time. Oh, it's perfect. So yeah, welcome to 390. This is probably as long as I'm planning to talk. We're going to mostly do stuff. That's why we're here. The Jupyter notebooks are up. Let me know how the installation of Conda goes. I will be here on Wednesday. We can just do this in person. And then as soon as you are comfortable with it, you can work from home. I'm perfectly fine with that. As you can see, the other 5 people in this class have decided to start doing that already. So that's OK. So yeah, this is what we're trying to do. We're going to try our first Jupyter Notebook. It is really easing us into the Python language. So it's really things like, how do I print hello world? You know, how do I assign variables? How is it stored in Python? Everything is a pointer. And so yeah, you'll just get eased into the language. We're doing a language class on the side. So okay, are there any questions? I can't be that clear. All right.
I'm sure they'll come up throughout the semester.
Oh yeah, no, that's what I'm bracing for. Okay, well, you got my email, you got the Blackboard, you know what to do. If you are going to do this on your own machine, try installing this, you know, try to do this as soon as practical because, yeah. You can just Google astroconda, for example, and it should get you to astroconda.readthedocs.io, and there you go. Let me know if you get into any issues with that. I will also post that on Blackboard, and I'm now going to hit stop recording. Am I? No. Is this? Ugh. I don't think this thing actually recorded properly. Oh boy. Great. Came in special, so I'm going to go see if Lutz actually got that.
Yes, who is it?
Venom. See if we actually recorded all this, because it looked like I was recording, but is it still recording? No idea. I'm still trying to figure out if I'm recording or not, because this thing went to sleep and logged out, so
That doesn't matter.
Okay.
Oh, yeah, I see what you mean.
So, well, we're going to see if this is going to end up online, or if I'm, you know, just putting the, I put the slides online, I put everything on the Blackboard, so it could be a complete self-study class, but yeah, okay.
It was recording.
Okay. All right.
Can I stop it?
Yeah.